morning, my dear students. This is K.P.T. Vijaya Bhaskar, Department of Chemistry, K.B.N College. Today, my topic is carbon-carbon pi bonds, alkenes and alkynes. Introduction. Alkenes are unsaturated organic compounds containing carbon-carbon double bonds. They are important feedstock for series of industrial chemicals, especially polymers. You know very well about polymers. Simple examples are ethene and propene that are important in industrial organic chemicals. The chemical activity of alkenes are mainly because of carbon-carbon double bond. Alkenes generally undergoes addition reactions at site of double bonds. The pi bond acts as source of electrons and may have electrophiles and usually involved in addition reactions to synthesize saturated compounds. See, carbon-carbon pi bonds, alkenes. So these alkenes are hydrocarbons containing double bonds between two carbon atoms are called alkenes. These are also called olefins. These alkenes are unsaturated compounds. Their general formula is CnH2n. See, for example, ethylene. You know very well about ethylene. The IUPAC name of the ethylene is ethene. The structure is CH2 double bond CH2. The second example is propylene. That is common name. The IUPAC name of the propylene CH3 CH double bond CH2. And another examples, butylene, it is also called 1-butene, and 2-butylene, it is also called 2-butene. With these examples, the next topic is general methods of preparations of alkenes. We have several methods available in our organic chemistry. The first one is by dehydration of alcohols. You know what are alcohols? Alcohols are organic compounds which contains the functional group OH groups. That means the general formula ROH. So alkenes are prepared by heating alcohols with concentrated sulfuric acid at 170 degrees centigrade or by sending vapors of alcohols over alumina formula Al2O3, that is at 350 degrees centigrade to 400 degrees centigrade, or by heating alcohols with phosphorus pentoxide or phosphoric acid. Say for example, when ethylene is prepared by heating the alcohol, ethyl alcohol with concentrated sulfuric acid at 170 degrees centigrade. See this equation, ethyl alcohol, the formula CH3CH2OH. This ethyl alcohol is heating with concentrated H2SO4 at about 170 degrees centigrade. In this reaction, water molecule is eliminated and then ethene is the final product. The second example is when 1-butanol is heated with concentrated H2SO4 at 170 degrees centigrade, gives 1-butene. So, by dehydration of alcohols, we can produce alkenes in industrial level. The second method is by dehydrohalogenation of alkyl halides. Generally, alkenes are prepared by the dehydrohalogenation. Dehydrohalogenation means removal of hydrogen as well as halogen. So, dehydrogenation of alkyl halides with alcoholic KOH or NaOH means when KOH or NaOH is dissolved in alcohol, it is called alcoholic KOH or alcoholic NaOH. For example, bromoethane, the formula is CH3CH2Br. When treated with alcoholic KOH or NaOH gives ethene. The second example is when 2-bromopropane, it is treated with the alcoholic KOH or NaOH, it will give propene. So by using dehydrohalogenation of alkyl halides, we can prepare alkenes in the industrial level. The third one is from alkynes. Alkynes are also hydrocarbons. They contain triple bond in between carbon atoms. So alkynes can be used for the preparation of alkenes. It is carried out by the reduction of alkynes with hydrogen in the presence of pelladized charcoal. This results in the formation of alkenes. See, for example, alkynes undergoes hydrogenation in the presence of pelladized carbon. It will give alkenes. Another example, ethane, when it undergoes hydrogenation in the presence of pelladized carbon, it will give ethene. The third example is when propane undergoes hydrogenation in the presence of a pelladized carbon, it will give propene. See, the alkenes obtained from the above reactions have cis geometry. See, cis alkene from alkyne, ethene and propene, these all are cis products. So they are cis geometry. In order to form trans alkenes, see in this reaction, the second one, when alkyne undergoes hydrogenation in the presence of sodium in the liquid ammonia, the product name is a trans alkene. So alkynes are made to undergo reduction with the sodium in liquid ammonia. The product name is trans alkenes. This is only the difference between cis and trans products. The next one, chemical properties of alkenes. Usually in alkenes, there is a double bond in between two carbon atoms. So alkenes usually undergoes additional reactions. So the double bond acts as source of electrons and hence alkenes react with electron deficient species. These species are known as electrophiles and may lead to electrophilic addition reactions. So alkene can also undergo free radical addition reactions and polymerization reactions. So addition reactions of alkenes. Under addition reactions, we have hydrogenation. Hydrogenation means addition of hydrogen. See, when alkenes are treated with hydrogen in the presence of nickel at 100 degrees centigrade or platinum or palladium, it will produce as alkanes. So in this reaction, when alkene, there is a double bond in between two carbon atoms. So this is alkene. When it undergoes hydrogenation in the presence of nickel, platinum or palladium, in the presence of hydrogen molecule, it will produce alkane. So the next property is halogenation, addition of halogens. See, alkenes are easily converted by halogens to alkyl halides, where two halogen atoms are attached to two carbon at adjacent positions. The reaction is relatively easily carried out at room temperature and does not require any physical parameters like light. So two reactants are mixed in an inert solvent such as carbon tetrachloride. So when ethene is going to react with the bromine, it will give 1,2-dibromoethane. The third one is addition of hydrogen halides. The pi bond is not as strong as the sigma bond and the electron cloud above and below the plane is polarizable. See, in this structure, the alkene contains double bond. Double bond means one sigma bond and one pi bond. So here, the pi bond when compared with the sigma bond is not as such a strong. So the electron cloud of a pi bond above and below the plane is polarizable. So this way a double bond can act as a nucleophile. A typical example of this mechanism is addition of hydrogen halides, where proton from strong acid may yield a carbocation. In the presence of strong nucleophile, carbocation undergoes electrophilic addition to the double bond site. So in the given example, when alkene is going to react with the hydrogen halide, the product is like this. Here, the answer is described by Markovnikov rule, which states that in the addition of an acid to the carbon-carbon double bond of alkene, the hydrogen of the acid attaches itself to the carbon that already holds the greater number of hydrogens. This rule defines the regioselectivity in the electrophilic substitution reactions, addition reactions. See, in this reaction, one propene when reacts with a asymmetric reagent like HCl, it will give 2-chloropropene. Here, the negative portion of the reagent added to the less hydrogen atoms of the carbon, and hydrogen is added to more hydrogen atoms of the carbon. So 2-chloropropane is the product. So the next one is ozonolysis. Ozone, the molecular formula is O3. It is a triatomic molecule and is powerful electrophile. It undergoes reaction with alkene, cleaving both sigma and pi carbon-carbon bonds. You know, carbon-carbon contains a double bond. In double bond, one is sigma and another one is pi bond. So this reaction is known as ozonolysis or ozonation, and the products are called ozonides. So when alkene reacts with the ozone, O3, it gives ozonide. Ozone is passed through an alkene solution in an inert solvent. The reaction leaves a viscous ozonide that cannot be purified as it is unstable and unexplosive in nature. So ozonides is immediately treated with water and in the presence of a reducing agent to form carbonyl compounds like ketones or aldehydes. So this is ozonolysis. The next one is Diels-Alder reaction. In Diels-Alder reaction, when conjugated diene is heated with unsaturated compound called dienophile, a cyclic compound called adduct is formed. So this reaction is called Diels-Alder reaction. In this equation, a conjugated diene is going to react with unsaturated compound such as dienophile. It gives a cyclic compound called adduct. For example, 1,3-butadiene, usually it is called diene, when it reacts with ethylene and a cyclic addition compound cyclic hexene. So 1,3-butadiene reacts with ethylene, a cyclic addition compound cyclic hexene is the product. It is also called adduct. So it is a Diels-Alder reaction. See another example, 1,3-butadiene and malic anhydride. It undergoes Diels-Alder reaction. Both compounds undergoes cyclization. It will give a product called adduct. So this is a Diels-Alder reaction. So the next one is hydroboration oxidation. So the hydroboration oxidation reaction is an organic chemical reaction that is used for the conversion of alkene into alcohol. In this reaction, boranes are boron hydrogen compounds are called boranes. The simple boron BH3 is added across the carbon-carbon double bond of an alkene, resulting in an organoboron compound. This organoboron compound reacts with hydrogen peroxide in the basic medium like NaOH and oxidizes to alcohol. So the regiochemistry of this reaction is such that the product formed during hydroboration follows anti-Markovnikov rule. That is, hydrogen goes to the more substituted carbon atoms of the alkene. The stereochemistry of this reaction is syn. That is, hydrogen and boron are on the same side of the product. So this is the reaction of hydroboration oxidation. In this reaction, alkene reacts with a boron hydrogen compound borane and then reacts with hydrogen peroxide in the presence of a basic medium NaOH. It will give alcohol and hydroxyborane. So this is the mechanism of hydroboration oxidation. In this reaction, the electrophilic boron attacks the pi electrons of the alkene and forms a bond with the carbon, resulting in the organoboron compound. So in the first step, organoboron compound is formed. In the second step, the hydrogen peroxide is deprotonated by the sodium hydroxide to give a conjugate base. In the third step, the deprotonated peroxide anion then adds to the organoboron which is formed in the first step, forming negatively charged organoboron species. In the fourth step, the organoboron species rearranges itself to a neutral compound. The nucleophile hydroxide attacks the boron and breaks the oxygen-boron bond, resulting in an alkoxide. Finally, the alkoxide is protonated by water to give an alcohol. So this is the reaction mechanism for hydroboration oxidation. Thank you.